But in this Harvard Gazette article, there were elements related to COVID-19 and the paradox of having lots of data. And then you also have a paper where this can happen with electoral surveys. So can you elaborate for us on how bias is amplified the larger the data set we have?
Yes. Well, thank you very much for asking that question. And in fact, the Gazette article was really about the one I already mentioned, the publication in the Nature on this COVID vaccinations. But let me backtrack a little bit because that's where I started, and I surprised myself after I'd done the calculation. This was, I think, the other in terms of electoral one is the 2018 article. What I did was I tried to quantify the data quality. Now, it's much easier to quantify data quantity, obviously, but it's much harder to quantify data quality. So I started this work actually really back in 2012, 2013. The department at the time had a visit, coming from U.S. Census Bureau by name of Jeremy Wu. And Dr. Jeremy Wu at that time made a presentation to my department, and he asked the following question, which I think is a really fun question for all the audience to think about. And if I have chance, I usually will question the audience, how would you answer that question? So at the time, and particularly now, there's a lot more of these cases that U.S. Census Bureau was thinking about, how do we utilize all these administrative data, right? There's lots of data are already there. And the question is, how do we use these data that we know they cover large percentage of a population, but they were not collected for statistical inference purpose. So they are not like a randomized, they're not a probability sample, right? So Jeremy asked the question to me and my fellow statisticians, like, if you're given a 5% data of a population, which we tell you that is a good quality, statistically valid in a random sample, versus 80% of the population data, which I just tell you it covers 80%, but I have no idea the quality of the data. Which one would you trust? Do you trust that 5% of the data, or you trust the 80% of the data, right? Of course, a statistician's first response would be, or should be anybody respond, would be trust for what purpose, right? Jeremy responds say, well, let's say we want to estimate the population average. For example, we want to estimate in the end how many people will vote for a particular candidate, right? So, most statisticians, the answer will be, I'd be trusting that 5% of the answer, because 5% of the data, because I know how to assess its uncertainty. I have all the formulas because it's a random sample, right? So Jeremy said, okay, that's fine, okay. But now I'm going to change the question. You still have the 5% of the probability sample, but the other one covers 90%. Do you change your mind? Now it's 90% versus 5%. 90% means I know it's covered 90% of the population, but I don't know its quality.
Right.
Well, some statisticians, myself included, start thinking, well, maybe 90% I probably should have switched. And there's people, some people still don't switch. Then Jeremy said, what about 95%? Right? At some point, he will say, wait, I had to switch because, by the time I get 100%, assume people answer responsibly, everything, 100% should be the right answer. Yeah. But that got me thinking. The Jeremy's question is, how do you measure the quality, of your data? Like, where do you do that switch? What's the calculation here? And that's a fascinating question, right? So that's how I started to do this work. And I eventually took years, actually. Eventually, this article published in 2018. And I did the following calculation, which was kind of mind-boggling, which really started my kind of journey about pushing people to think about the data quality issues. So I did the following calculation using 2016 data. I can estimate in 2016 data how correlated people's response to say whether they vote for Trump or not, and their willingness to participate in a survey. Okay, so the idea is that correlation should be zero if people just answer honestly, because it shouldn't be that say you look and say, because I'm going to vote for Trump, therefore I don't want to tell you. That creates bias, right? So we estimated, because after 2016 we know the answer. So we estimated what was that correlation. The correlation turned out to be minus 0.5%. Okay, it seems very tiny, minus 0.5%. Minus because the answer people tend to not respond are the ones who want to vote for Trump. So it's a negative sign.
Right.
It turned out that the minus 0.5% essentially caused a tremendous loss of effective data size. By which I mean the following: well, I did a rough calculation. Before the election, there were so many surveys out there. I did a rough calculation. It's about amounts to we had about 1% of the voting population, eligible voting population, provide their opinion. Let's say that's 2.3 million people. That's about 2,300 surveys, each with 1,000 people. But if I do the calculation, what's the effective sample size? Meaning like the statistical information in that 2.3 million answer, which sounds a lot. What's the equivalent answer if they did not have any defect? It's like coming from a true simple random sample. The answer is a surprising one. The answer, this is published in the article, is about 400 people, right? So basically, the 0.5% negative correlation caused a damage, which essentially lost about 99% of the data. Like the statistical accuracy.
99%.
Right. The statistical accuracy, we can show mathematically, is equivalent to you have the same answer from like 400 people without that bias. Okay.
Right.
So that was the calculation. And so I carried the same calculation for that COVID, a study done by the Facebook. And what we did a calculation is they have 250,000 people, but in the end, that because the correlations they have, that compared to the CDC, the benchmark, their sample size is essentially anywhere from like 10 to 250, compared to 250,000. So that's kind of a thing what I call the big data paradox, because it comes with two parts. Not only you have a tremendous reduction of the sample size, because you have so much data, and if you did not realize how small the data size is, if you just do the traditional confidence interval calculation, right? Because you want to give error bars, your error bar will be way too small, right? Because you use this erroneous sample size. So your error bar is so small, you will actually, the more data you have, the more you'll be centered at the wrong place. You will make sure yourself you never get to the right place, right? This is what I meant by the big data paradox.
Right.
Because the larger the data size, the more sure your answer is, but you're centered at the wrong place. Your confidence interval literally shrinks as the sample size goes up. You actually you have a higher and higher chance to prevent yourself to get to the right place at all. That's the big data paradox.
This is something I think about a lot as we have lots of data. And so this is something that impacts me all the time. If you try to use statistical approaches, like frequentist statistical approaches that were developed over 100 years ago.
Yeah.
So, the common way to get those error bars would be to say divide by the square root of the number of samples you have.
Exactly.
And when you're dealing with millions of data points, that means that your error bars they don't exist. Right. You're saying, I know exactly where we are.
Right.
Yeah.
But yes, you know exactly where you are, except you're at the wrong place.
Right.
So the whole paper I wrote is to really show these calculations. And speaking with these frequentist methods, they're based on a fundamental assumption, which is that the data are well mixed. It's a probabilistic sample, right? And so that's where
Right. So we're taking techniques where we explicitly say, and even if you're in an introductory statistics class as an undergraduate student, you're saying, okay, this statistic, it only applies if you have a representative random sample. But then we're constantly using that today in situations where we don't have a representative random sample.
Right, we know we don't have it. Yeah. Right, because and the thing, I guess, in my 2018 article, it's also available online. I think the surprising part, even some of my statistical colleagues are still debating with me. But what my calculations show is what matters is no longer just the sample size, is the relative sample size, how the sample size divides by the population size, and the larger the population, the worse you will end up with, and that's to a layperson that's not surprising, right? The large population is harder to analyze, but statistically, I was using the following analogy to help the general population to understand why the statisticians at the very beginning say we can ignore the population size, right? It's very much like when you taste a soup. If you're tasting soup, if you have a well mixed soup, right, regardless the size of the container, all you need is just a couple of spoons, right? Because you can taste how salty it is, how delicious it is. As long as the soup is well mixed, you don't really need that much. But if the soup is not well mixed, then you can see the size of the container really matters, right? Because the larger the container, the more chances there's some salty chunks are somewhere else, right? And so once you lost this kind of a well mixed assumption, that's essentially is what it is. It's well representativeness, the homogeneity. Then the problem becomes a lot harder. And the problem these days is the social media data, particularly is because of self-operating data, right? You cannot really randomize people. Say you go on this Twitter, you go on this Facebook. You don't. That doesn't happen. Right? You lost the control in terms of statistical kind of a control, and so then you really have to be careful. We all knew these things, but we all hope these problems are not that big. But what I did was just to show how seriously the problem is, because it really kills 99% even over the amount of data. And you can just do this mathematics. It's just out there.